All right, running an interactive job. Running an interactive job does use the qsub command, but you specify a -I for an interactive session. If you just run a job like this with qsub-I with no other options, you're just going to get the default job settings. And that's going to be one core on one node with only 1 GB of RAM for 30 minutes. The max wall time will be 30 minutes. That's all you get if you don't specify anything else. And that's the same for both an interactive job or a batch job. No matter what kind of job you submit, if you don't specify what you need, you're just going to get the defaults. And those defaults are pretty limited. When you submit an interactive job, you can specify all kinds of things, just like a batch job. You can specify your wall time. You can specify the number of nodes you want, the number of cores, and so on. Now I'm going to submit an interactive job right now. All right, qsub-I-L select equals 2 in CPUs equals 8 MPI prox equals 8, and then equals 3 GB. And I'm going to specify an interconnect mirrornet and a wall time of 1 hour. And that's my interactive session command. Let's see if it works. All right, it was accepted by the PBS system, so I was assigned a job ID number, so it was a valid command, and it has just started. And I've been logged into node 1462. Now, in my request, I requested 2 nodes with 8 cores on each one of those nodes. And the node that I'm logged into is just the master node. As with my previous job, in that other job, I was running on multiple nodes, but the very first node in the execution host list, that's considered the master node. So with an interactive session, even if you have multiple nodes, you're going to be logged into your master node. And so now I have this parallel environment available to me. I've got 2 nodes. I've got 8 cores on each node, 8 parallel tasks available for me to use, 3 GB of RAM on each one of those nodes. So I've got a total of 16 cores and 6 GB of RAM. And I'll go into my intro Palmetto directory, and I'm going to compile and run some serial code and some parallel code. So I'm going to use module add Intel. Let's see. Let's look at what's available. Module avail. Let's try module add Intel 12.0 and impitch to 1.4. All right. So I have those 2 modules loaded. Now I'm going to compile a serial program. There's a very simple program here, and it's also presented in the slides. It's called gethostname.c. Very simple C code. Essentially, all it does is it prints the name of the node where I'm currently running the program. That's all it does. It's ridiculously simple. So let's compile that. I'm going to compile with the Intel C compiler. Gethostname.c. My output file, I can call it anything I want. I'm going to call it gethostname.exe. Compiling. If I do an lsltr, I can see that my new gethostname.exe file has just been created. That's my new executable. Now I can run this from my interactive session. I'm not logged into the user node. I'm actually logged into a compute node. So it's okay for me to run my computational programs here. I'm going to run my gethostname program that I just created. That's it. Very, very simple. So now let's try a parallel version of the same thing. In case you wanted to run that same job in a batch mode, this is what the job script would look like. Very simple job script. So here's the same code, but this code has been parallelized. It's got additional code added to it to make it run in parallel, and it will run across however many cores I make available to it. Here I'm just including the MPI headers. I'm pulling in any arguments passed on the command line. I'm not passing any arguments on the command line, but this is just something that's required by MPI. I'm starting up MPI, starting up parallel communication. I'm getting the process ID number for each one of my tasks. And then at the end, I'm going to close down parallel communication. All right, so let's compile and run that example. Instead of compiling with the Intel C compiler, I've got to use a parallel compiler, and that's going to be the MPI-CC compiler. That's made available by when I added the impitch module. The name of my source file is gethostname.mpi.c. I'm going to specify an output file, gethostname mpi.exe. All right, I just compiled my code, doing lsltr. There's my new parallel executable, ready to run. To run a parallel program, I have to set up my parallel environment and then run the executable. I'm going to do that with mpi run. You can use either mpi run-np and then the number of cores and then the name of your executable. It's got to be a parallel executable. So you can either use mpi run, and there's the output, or you can use mpi exec. These are both wrapper scripts that set up the parallel communication. They're both made available by newer versions of impitch, and they both do exactly the same thing for all intents and purposes. See, it's pretty much the same. Notice each time I ran that parallel program, the individual tasks, the individual MPI tasks, reported back in random order. I'd have to modify the code to force them to come back in order. They're just reporting back in whatever, depending on how quickly they're able to get their response back to the master node. All right, so that's compiling and running a serial program, and then compiling and running a parallel program, all in an interactive session. Once you had tested your code in an interactive session, then you'd be ready to put together a batch job script and submit your job to run over the weekend or overnight or something like that. Also, if you wanted to see what a job script for that simple example looked like, this is what a job script for that get host name program would look like. And this is the same job script, but here we're using that number of cores variable that I set in some of my job scripts, in case you want to see the difference between without and with that variable. Something that I want to draw your attention to in this example, the way I'm using that variable declaration here, the way I'm calling that variable, when that variable stands alone with white space on either side, I'm using the $n-cores because bash will easily recognize that that's a variable. However, when I'm using the same variable embedded amongst other characters, when I'm creating this file name, I'm using the curly braces around it just to make sure that bash recognizes that that's a variable and not just part of this text. All right, so I've got some other examples here, but you're welcome to run on your own. This pi estimation can be run in serial as well as parallel.